So get this, a problem solved in seconds, literally seconds. And our best regular computers, they take, what, 10 septillion years?
It's completely wild, isn't it? Or like, how can one thing be in two places at the exact same time?
Right. It makes no sense classically.
Exactly. And that's the kind of mind-bending stuff we're getting into today on the Deep Dive with Milo and Avery. We're trying to cut through all that quantum complexity.
Yeah, the question is, how is this unseen edge of computing going to reshape your world? Not just someday, but like now.
Okay, so today's deep dive, it's all quantum computing. What is it fundamentally? How does it actually work?
And crucially, how is it moving out of the physics labs?
Yeah.
We're talking real world stuff, medicine, logistics.
Even cybersecurity, yeah.
Yeah.
Our mission today is basically to navigate this, find those surprising bits, those aha moments that really show why this tech is, well, potentially transformative.
Okay, so let's start at the beginning. Your phone, your laptop, they run on classical bits, right?
Right. Simple binary choices, 0 or 1, off or on. And information gets processed step by step, sequentially.
Pretty straightforward.
But quantum computing, it takes this sharp left turn, the basic unit, the qubit. It's different.
Okay, how different?
Well, it's not just 0 or 1. A qubit can be 0, it can be 1, or, and this is the mind-bending part, it can be both at the same time.
Both. Simultaneously.
Yeah. Think of a coin spinning in the air. Before it lands, is it heads or tails? It's kind of both until you measure it, until it lands.
Okay, that spinning coin analogy helps a bit. So that ability, being multiple things at once, that's the key.
That's a huge part of it. It's called superposition.
Right, superposition.
Yeah.
So if qubits can be 0, 1, and both, how does that work in reality? How can something be in multiple states?
It is fundamentally counterintuitive, no doubt. The physicist Richard Feynman basically said it contains the only mystery of quantum mechanics.
So no easy classical explanation.
Nope. There's no intuitive explanation in our everyday terms. But what it allows is for a quantum computer to explore tons of possibilities all at the same time.
Instead of checking them one by one like a classical computer?
Exactly. Think of waves in a pond overlapping, creating this really complex pattern. Or how polarized sunglasses work, light exists in a superposition of states until it hits the filter.
Okay, so it's like parallel processing on a whole different level.
You got it.
All
And
right.
then it gets even weirder.
Oh, great. Weirder how?
With entanglement.
Hmm.
Einstein called it spooky action at a distance.
Spooky. I like it. What is it?
It's where two or more qubits become linked, like deeply correlated. If you measure the state of one, you instantly know the state of the other, no matter how far apart they are. Miles, light years, doesn't matter.
Instantly. Across distance.
Instantly. It creates this highly interconnected system. And having these entangled qubits, that's what gives quantum computers this potential for exponentially greater processing capacity.
So superposition lets them explore possibilities, and entanglement links those explorations together.
Kind of, yeah. Entanglement is seen as a necessary ingredient for any quantum computation that truly outperforms a classical one. It's this deep connection that unlocks the power.
Okay, so why does all this quantum weirdness matter now? Classical computers are pretty powerful these days.
They are, but they process things linearly, step by step, and that creates bottlenecks, especially for problems that don't just get bigger, they get exponentially more complex.
Like what kind of problems?
The classic example is the traveling salesman problem. Find the shortest route hitting, say, 40 cities.
Okay, that's simple enough.
But the number of possible routes, it's 8.15 times 10 to the power of 47, an unfathomable number.
Whoa.
Yeah. A classical computer, even a massive supercomputer, has to basically try them out one after another. Brute force. It would literally take longer than the universe has existed.
So classical computers just hit a wall.
For those kinds of problems, yes. They process too slowly, too sequentially.
And quantum computers, they don't hit that wall.
Because they can explore multiple possibilities simultaneously thanks to superposition and entanglement, that makes them exponentially faster for these specific complex problems.
Exponentially faster. We keep hearing that. Have we actually seen it?
Oh, yeah. We've seen demonstrations of quantum supremacy or beyond classical computation. Remember Google's Sycamore processor back in 2019?
Vaguely. What did it do?
It solved a very specific, tailored problem in 200 seconds. The estimate then was that the best supercomputer would need 10,000 years for the same task.
Okay, 200 seconds versus 10,000 years. That's significant.
But get this. They reran a similar experiment more recently with their newer Willow chip, the task that took Sycamore minutes. They estimate it would now take a classical supercomputer 10 septillion years.
10 septillion. That number doesn't even sound real.
It's astronomical. It shows the quantum advantage isn't just linear. It's growing incredibly fast as the hardware improves. And it's not just Google. D-Wave had a quantum computer solve an optimization problem 100 million times faster than a classical one.
Turning a 10,000-year problem into 1 second.
Exactly. It's a fundamental shift for certain calculations.
Okay, the numbers are just staggering. But let's bring it down to earth. What does this mean for, say, an actual patient in a hospital? How does this tech help us?
Well, the potential in healthcare is genuinely exciting. Take diagnostics. Quantum-enhanced AI models have hit like 98% accuracy classifying skin lesions.
Better than doctors using current tools.
Significantly better than standard computer algorithms, which were maybe 81, 97%. That could mean much earlier cancer detection or better surgical planning for tricky tumors.
Wow. Early detection is huge.
Totally. And there are ideas for using it to rapidly spot abnormal cells in pathology slides, too. Plus, think about drug discovery.
Simulating molecules.
Exactly. Quantum computers could simulate molecular interactions with unprecedented accuracy, potentially speeding up the discovery of new drugs massively, and even personalized medicine algorithms tailoring treatments based on your specific data.
Okay. Better diagnosis, faster drug discovery. What about in the moment, like during surgery? Is it fast enough for real-time decisions?
That's the cutting edge, but yes, potentially. Imagine a neurosurgeon removing a brain tumor, a glioblastoma.
Okay. Extremely delicate.
Right. Quantum algorithms could potentially integrate all the complex scan data MRI, DTI, fMRI with what the surgeon is seeing right then in real time.
To give them a super precise map during the operation.
Exactly. Guiding them to remove the tumor while minimizing damage to healthy tissue far faster and more precisely than current tech allows. That could dramatically improve outcomes.
Okay, that's incredible potential in medicine. What about other areas? You mentioned logistics.
Yeah, quantum really shines with these complex optimization problems, like untangling supply chains. Remember the container ship backlogs during the pandemic?
Chaos.
The Port of Los Angeles actually used a quantum optimization engine to help sort out that mess, figuring out better ways to sequence container moves and truck dispatches.
So making things flow better.
Precisely. And companies like BMW are using it to optimize their global supply networks, getting parts where they need to be more efficiently.
What about balancing different goals?
Yeah.
Like cost versus speed versus being green.
Another sweet spot. Quantum algorithms can handle multi-objective optimization. One study looked at optimizing taxi dispatch.
Okay.
Using quantum methods, they found they could provide the same level of service with 30% fewer vehicles.
30% fewer taxis.
Yeah. Think about it, lower costs for the company and lower carbon emissions. It's also expected to help design better batteries, optimize power grids, manage energy distribution.
And discover new materials, right? Like super strong but lightweight stuff.
Exactly. Material science is another huge area.
This power is just immense. Which naturally makes me think, what about security? Our digital lives are built on encryption.
Ah, yes. The double-edged sword, as they say.
How so?
Yeah.
Villain first.
The villain is an algorithm called Shor's algorithm. If you run it on a powerful enough quantum computer, a cryptographically relevant one, it can break the encryption we use today, RSA, Diffie-Hellman. The stuff protecting banking, emails, everything.
Break it how?
Current encryption relies on the fact that factoring huge numbers is incredibly hard for classical computers. Like, takes longer than the age of the universe hard.
But not for a quantum computer.
Not for one running Shor's algorithm, no. It makes factoring those large numbers feasible.
So all current encryption is potentially vulnerable. That's terrifying.
It is. And the immediate worry isn't just about future attacks. It's about harvest now, decrypt later.
Harvest now. What does that mean?
It means bad actors are potentially copying and storing encrypted data right now. Data that's safe today.
Waiting until they have a quantum computer powerful enough to break the encryption later.
Exactly. Your secrets from today could be exposed years down the line. The NSA is definitely worried about this possibility for national security.
Okay, that's genuinely chilling. So if quantum is the villain, how is it also the hero?
Thankfully, the same physics offers solutions. We're developing quantum-safe encryption. Things like quantum key distribution, QKD, and post-quantum cryptography, PQC.
New types of encryption that even quantum computers can't break.
That's the goal. Designing new cryptographic standards that are resistant to both classical and quantum attacks. It's a race, basically, to upgrade our security before CRQCs become a reality.
Is there time?
Most experts think commercial uses of quantum computers will likely emerge before someone can use them to break strong encryption on, say, classified data. So, yes, there seems to be a window, but we need to act on deploying PQC now.
Okay, this all sounds like sci-fi becoming real.
Yeah.
But there must be catches, right? What's stopping this from being everywhere already?
Oh, plenty of catches. The biggest one right now is the hardware itself. It's still in its infancy.
How so?
Most machines we have are called NISQ machines, noisy intermediate scale quantum. The noisy part is key.
Noisy means prone to errors.
Exactly. Qubits are incredibly delicate. Any little vibration, temperature change, stray radiation, what scientists call noise or decoherence, can make their quantum state collapse, ruining the calculation.
Like trying to build a house of cards in a hurricane.
That's a pretty good analogy, yeah. To do really long, complex, error-free computations, we need logical qubits.
Logical qubits. As opposed to...
Physical qubits. You need potentially millions of these fragile physical qubits working together with error correction codes just to create maybe hundreds or even just a few stable, reliable logical qubits.
Millions for hundreds, wow. So we're not there yet.
Not even close for large-scale, fault-tolerant machines. That's why a lot of current research is theoretical or uses simulations. We are making progress on the hardware, though, improving the connections, the gates between qubits. Some experiments show up to 98.3% fidelity.
That sounds pretty good.
It is good, but imagine a calculation with 1,000,000 steps. Even a tiny error rate at each step compounds really fast. So yeah, hardware limits are still the main bottleneck.
Okay, hardware's a huge challenge. What else?
Another big one is just writing the programs, algorithms. It requires this really deep, specialized knowledge blending quantum physics with computer science and often operations research.
And there aren't many people who have that specific skill set.
Exactly. The talent pool of quantum experts is still pretty limited. That slows down developing useful applications.
Makes sense.
And then, of course, there's the cost.
Ah, yes. Always the cost.
Building and maintaining these machines is incredibly expensive. Cutting-edge tech always is. There's a real risk of a quantum divide where only huge companies or governments can afford to play.
So smaller companies or researchers might get left behind.
That's the concern, but there is a counterpoint here.
Which is?
The cloud. Companies like IBM, Amazon, Google, Microsoft, they're offering quantum computing access via the cloud.
So you don't have to buy the multi-million-dollar machine yourself.
Right. It's more of a pay-as-you-go model. It makes it much more accessible for businesses and researchers to start experimenting, testing algorithms, seeing what's possible without that massive upfront cost. Still not cheap, mind you, but way more doable.
Okay, so looking ahead then, peering into the quantum crystal ball. What's a realistic timeline? When do we see more widespread impact?
Well, in the short term, say, the rest of this decade, until around 2030, quantum computers will likely stay mostly as cloud services. People will be experimenting, developing algorithms, finding those first niche applications.
Like what kind of applications?
We might see early breakthroughs in designing new materials, maybe high-temperature superconductors, optimizing specific AI models, perhaps some novel medical diagnostics using quantum sensors linked with AI, basically achieving quantum advantage for very specific narrow tasks. Bill Gates even thinks we'll see usefulness in just 3 to 5 years for certain problems.
Okay, short term is niche advantage. What about medium term, say 2030 to 2040?
That's when things could get really interesting. That's the time frame many experts predict we might see the first quantum computers with error correction, true fault-tolerant machines.
The ones with stable logical qubits.
Exactly. If that happens, if we get machines with potentially millions of physical qubits forming reliable logical ones, then you could see revolutions.
Revolutions where?
Biotechnology simulating entire human cells. Chemistry designing completely new molecules and catalysts from scratch. Finance optimizing global investments in ways we can't even imagine now.
And maybe AI.
There's definitely talk of quantum artificial intelligence, maybe even a synergy with artificial general intelligence or AGI, but that's still pretty speculative.
It's still crucial to remember, though, right? This isn't about replacing your laptop or phone.
Absolutely not. Quantum computing is designed to complement classical computers, not replace them. It's a specialized tool for those incredibly hard, specific problems that classical machines just choke on.
A very powerful, specialized tool.
Exactly. Which brings us back to the importance of doing this right. As we head into this quantum future, responsible development is critical. Meaning we need to be rolling out that post-quantum encryption now. We need to invest seriously in education to build that talent pipeline.
And set some ground rules.
Yes. We need regulatory frameworks, ethical guidelines. We need to think hard about ensuring this powerful technology is developed responsibly and that access is equitable. We need to maximize the good and minimize the potential harm.
What an incredible journey. It really does feel like we're on the cusp of something huge, a totally new way of computing.
It absolutely does. It's complex, sure, and definitely mind-bending sometimes, but the sheer potential to solve problems we used to think were fundamentally unsolvable. It's just exhilarating.
The future really is quantum, isn't it?
It seems like it's being built block by block, qubit by qubit right now. It makes you wonder what impossible thing it'll crack next.
Definitely food for thought. Thanks for diving deep with us today on The Deep Dive with Milo and Avery.